Hello everyone. Welcome to this presentation called Interpolation Schemes for Convective Terms in Conservation Equations. My name is Hugo Castillo Sanchez, and in the previous videos that I have uploaded in this channel, we have focused on explaining algorithms for the solution of the Navier-Stokes equations, where we have to discretize the temporal, convective, diffusive, and source terms. Also, in those videos that can be found in my channel, I have also explained how to treat mathematically those terms, with the exception of the convective terms, because they are slightly more complicated and they need a special treatment. So for this reason, I wanted to create this video to focus only on those terms. But I also will not focus on the Navier-Stokes equations. I also want to consider other conservation equations, such as the energy and mass conservation equations. So the overview of this video, I will start by talking about convective terms in conservation equations and their importance in CFD, and then I will move to explain how to discretize those terms, and then I will give a brief introduction to some of the interpolation schemes and the most popular ones used in CFD. So just a quick reminder. So in CFD, we are interested in solving the Navier-Stokes equations, but I'm only interested by now in the case of incompressible fluids. So these equations express, the Navier-Stokes equations express mathematically the momentum and mass conservation for Newtonian fluids, which are the simplest fluids that can be modeled mathematically speaking. In a Newtonian fluid, we observe a linear relationship between the shear stress and the shear stress with constant viscosity. And for these fluids, for incompressible fluids with constant physical properties, such as density and viscosity, we have these two systems of equations, which are the mass conservation equation, which is just the divergence of the velocity field that has to be equal to 0. And then in momentum conservation equation, we have Newton's second law for fluids, where we have on the left hand side, we have two derivatives. One is the temporal derivative of the velocity field, plus we have a spatial derivative, which is the velocity field multiplied by the gradient of the velocity, all of this multiplied by the density, and that has to be equal to the forces applied to the fluid. We have a pressure gradient, we have a Laplacian of the velocity field, and then the source term, which considers the presence of external sources of movement, such as gravitational effects, electromagnetic fields. And I want to focus right now on the momentum conservation equation. I want you to see these other two equations, which are conservation equations used in CFD. So in equation 3, we have the momentum conservation equation, which is expressed in dimensionless form. You are probably with this dimensionless number, which is the Reynolds number, that compares convection with diffusion of momentum. And then you can notice that equation 4 and equation 5, these equations look very similar, mathematically speaking. And here we have in equation 4 the energy conservation, and then in equation 5 we have mass conservation equation. You can notice that these three equations are very similar. Each equation has a temporal derivative. This equation is written in terms of the temperature, and this equation is written in terms of concentration of species A. And then we have each equation also has a convective term. That means we have the velocity field multiplied by the gradient of a property. In momentum conservation, we have the velocity, we have gradient of temperature for the energy conservation equation, and for mass conservation, we have gradient of the concentration. And then on the right hand side, we have a Laplacian, in this case the velocity, here the temperature, Laplacian of temperature, and then here in mass conservation, we have a Laplacian of concentration. And then we also have a source term. I already explained the source term in momentum conservation equation. in energy conservation we can have external sources of heat or external sources of energy, for instance. Or this term can also consider losses of energy. Here in energy conservation for fluids, we might have a viscous dissipation. That means we might have energy losses due to friction. And then we also have, for mass conservation, a source term, which means, for instance, how we can obtain new mass from a species A. And the only way that we can obtain mass is through a chemical reaction. Because remember, mass conservation tells us that the same amount of matter exists before and after a change. No, the mass is not created and not destroyed. It has to come from somewhere. And also these conservation equations express different physical laws. I already talked about Newton's second law. Newton's second law for fluids. Energy conservation is just the first law of thermodynamics that tells us that internal energy changes are equal to heat applied into the system plus work done on the system. And mass conservation is something similar. The only way we can obtain mass is through a chemical reaction or internal changes in the concentration. And yeah, I forgot to say that this equation is expressed for any species because we might have, for instance, a mixture of multiple species, and then we have to solve a mass conservation equation for each of these species. Oh, and yeah, I also forgot to mention that each equation has a different dimensionless number. For momentum conservation equation, we have the Reynolds number. And I like to say that we have this number and this one as well. I like to say that this number is a cousin of the Reynolds number because they are very similar, but they express different physical phenomena. In the case of the Peclet number, is the equivalent of the Reynolds number, but in energy conservation, Peclet only compares transport of energy by convection, and Peclet compares it with energy transported by diffusion. And here for the mass conservation equation, we have the Peclet of mass number, which expresses it compares the transport of mass by convection with the transport of mass by diffusion. And the goal of this presentation is to talk specifically about these terms, which are the convective terms, which gives these terms give the non-linearity to the conservation equations. Also, these equations describe the transport of the property. It can be either velocity, temperature, or concentration. So convective terms describe the transport of these properties due to the bulk fluid motion. For instance, it's a bit hard to visualize transport of momentum by convection, but we can say that this term describes how the velocity transports itself. Also, for instance, this is a temporal derivative. No, this is an spatial derivative that tells us how the velocity changes spatially in the direction of the flow. So another example to understand this process of convection, I like to use, for instance, the example of when you are in a mall or in a supermarket and you are in the first floor, and then you want to use you want to go to the last floor at the very top of the building. So you will use either an electric chair or an elevator or a lift. So you will take this mechanical device, and then it will commute you from the bottom to the top. So imagine that you are the property. So this electric stair or the elevator will transport you from the bottom to the top. So this is some sort of convection that you are being transported by the elevator, by the lift. So in conservation equations, we have something similar. For instance, the convection, transport of mass by convection. Let's say you are in a river, and then you add some bag of salt, and then the salt will be transported by the water from the river from one direction to another one. So water, the concentration of water will change as the as the as the river moves, as the river flows. And for those of you that have already taken energy heat transfer courses or energy transfer lectures, you are probably very familiar with natural convection. So natural convection is, for instance, is that transport of heat due to the difference in density of a fluid caused by temperature gradients. So this natural convection phenomena, you can observe it at your home. Let's say you want to heat some water in a kettle. So you will use a source of heat, and then you will start heating the kettle. And then the water that is in contact with the heat, it will get warmer. So the density of that fluid will decrease. So this low density fluid will start to go to the top of the surface. So it will carry with itself some heat. And then at the top, the fluid that was initially at the top is now going to be displaced to the bottom. So that fluid at the top will have a higher density, but now is being displaced by the low density fluid. So the high density fluid will now go to the bottom. And also it will also get warmer, and its density will change. So this causes a natural circulation from bottom to top and from top to bottom. So natural convection is a flow whose motion is caused by some parts of a fluid being heavier than other parts. So this is just an example of a convection, transport of convection, transport of energy by convection. I was talking about energy. So these terms can usually be ignored when either the Reynolds or the Peclet numbers are very small. And in some cases, it's really convenient to not to consider these terms because they are strongly nonlinear. So these equations are sometimes really hard to solve because of the convecting terms. So sometimes it's convenient to not consider them. So yeah, you can ignore them when these dimensionless numbers are very small. However, that's not always the case. Sometimes we have to consider them. So we have to tackle this issue. We have to find some way to treat them mathematically. So these convective terms are really important to study the nonlinear behavior of fluid flows. And they are especially relevant in turbulent flows. So, turbulence is that chaotic flow that is observed when you have a really high Reynolds number, or when you have a combination of high density fluid, high velocity flows, the height of the channel is really high, and you have small values of viscosity. So in order to explain how to treat these convective terms in CFD, I will use the finite volume method because it's the most popular numerical method to solve these conservation equations. So remember, in the finite volume method, we will solve each of the conservation equations in each conservation equation in each of the cells of our domain, or in each control volume of our domain. So let's say this is our whole domain, and then we will split it in 6 different cells or control volumes, and then we need to estimate the values of the properties, either the velocity, the temperature, or the concentration, at the centroids of each of the cells of our domain. So each of these cells will have 6 surfaces, 6 faces. So for instance, let's focus with this cell that has a centroid P. So this cell has 6 faces, and each of the faces will have a normal vector that will point out outside of the control volume. And then each face will also have a given surface. So the convective terms in the Navier-Stokes equation, so remember we want to study these terms and treat them mathematically. But for my explanation, it's really convenient to express those convective terms as this with this expression. So we have the divergence of this is a convective flux of momentum, which is just the product between density and twice the velocity field. So if you apply the chain rule to this term, you have these two terms. You have the velocity field multiplied by the divergence of this term, of this product, plus the velocity multiplied by the density, multiply the inner product with the velocity gradient. But we can simplify this equation if we consider the incompressibility condition and if we assume constant density. If we have these two conditions, this term that appears here is going to be equal to 0. So equation 6 becomes equation 7. So that means that the divergence of this term is equivalent to the product between density and this spatial derivative, which is the one that we have here. So this is just something I wanted to mention. Remember, this is only valid if we have incompressibility condition and constant density. So in the finite volume method, we use the divergence theorem or the Gauss theorem, which allows us to transform a volume integral into a surface integral. So remember, in the finite volume method, we applied a volume integral over the conservation equations, and then we will solve that volume integral in each of the cells of our domain. So here, for instance, I already explained this in one of my previous videos, but just as a quick reminder. So here, remember this term that is between brackets is the convective flux of momentum in each point of our cells. If you obtain the divergence of a flux, you will obtain a flow of momentum in each point of your volume, of your control volume. And then if you sum that quantity over your volume, over your control volume, you obtain the total momentum that is being transported by convection. And that has to be equal to this surface integral. That is just the convective flux of momentum that goes through all the faces of your control volume. So that is just basically the physical meaning of the divergence theorem. So again, the total the total momentum that is being transported by convection has to be equal to all the convective flux of momentum that crosses each of the faces of your control volume. So here in the surface integral we have this product, which is the convective flux of momentum multiplied by the unit normal vector that points out of the control volume. Remember, this is the unit normal vector that will point out outside the control volume. And this vector n is different for each of the faces of the cell. So this surface integral can be simplified even further. I'm not going to do all the maths. You can find the whole method to simplify this surface integral if you check the doctoral thesis of Dr. Hazak. That was one of the researchers that implemented this finite volume method in OpenFOAM, the one that developed this finite volume method. And this surface integral will have to be evaluated in each of the phases of the control volume, and assuming that the velocity varies linearly through the cell phases, this integral can be calculated, can be computed as this one, as this expression, where S is the surface of each of the phases of the cell. Then you have to multiply by the unit normal vector, and then you have to multiply by this product between density and velocity. But this velocity has to be evaluated at the phases of each of the at each of the phases of your cell. So this is another advantage of using the finite volume method, that you will have to evaluate those properties at the cell phases. So that's why this index appears here. It represents phases. And then you have to multiply this product by the velocity field at the phase. And then you sum this quantity in each of the phases of your control volume, and then you have this integral surface, which we already know that is equivalent to this volume integral. So in OpenFOAM, they use this notation. Instead of expressing this surface integral as equation 9, it usually appears as this equation 10, where F is the convective flux that is computed at just this vector, which is just the product between the surface and the unit normal vector, and then you have to multiply this vector by this quantity at the phase, at each of the phases of your control volume. And we can generalize this equation for other conservation properties. For instance, this equation 11 is in terms of phi, where phi can represent temperature for energy conservation, or it can also represent the concentration of a species, Ca, in case we are solving the mass conservation equation. So yeah, the equation 11 is the representation, the volume integral expressed as a surface integral for a conservative property phi. So as I already discussed before, we need to evaluate, once that we apply this mathematical treatment that we explained here, remember, we need to evaluate the velocity field, or either the temperature or the concentration at the cell phases, to evaluate the integrals. However, remember, in the finite volume method, our equations are defined at the centroids of the cells. So this is a problem. So in order to solve this issue, we need interpolation schemes that can give us an approximate value of the properties at the cell phases using the known values of the cell centroids. That means that in order to evaluate these quantities, we need to use an interpolation scheme that will use the values at the centroids of the cells, to evaluate the values of the property at the cell phases. So there exist different interpolation schemes. One of the most popular is the central differencing, but you can also find in the literature the Upwind differencing, blended differencing, linear Upwind, quick, cubista. But in this presentation, I just want to explain the basics of these interpolation schemes. So I will focus only on explaining briefly the schemes that use only the nearest neighbor cells of the control volume with centroid P. So that means that in order to evaluate the values of the properties at these cell phases, we will only consider cells that are close to this surface. So let's start with the simplest one. We have the central differences interpolation scheme. So we will assume, for this scheme, we assume a linear variation of the velocity at the cell phase between the centroids P and N, and then the value at the cell phases will be computed using this equation 12, which is known as the central or linear differencing which is usually called CD. So here we have two cells. So remember, we have to evaluate the values of the velocity at the cell faces. So we will use this equation 12. That you can see that depends on the value of the velocity at the centroid P and the value of the velocity at the centroid N. But you can see that we also have another constant, another parameter, which is fx, which is called an interpolation factor, which is bounded between 0 and 1. And this interpolation factor is just defined as a ratio between two distances. So here I have the location of our cell face, I have here the location of the centroid P, and here I have the location of the centroid N. So this fx is just a ratio between the distance between the face, between the cell face, this one, and the centroid N. So it's represented with a hat Fn, which is at the top. And then we have to divide it over this distance between the centroid P and the centroid N. So equation 13 allows us to calculate the interpolation factor. So this is a general equation, but it can be simplified if the cell size is the same for all cells. So that means that it is the size of this cell is equal to the cell size of this cell. So this equation, equation 13, the interpolation factor becomes 0.5, and then this equation 12 becomes equation 14, which you can see is some sort of an average between the values of the value at the cell face is just an average between the velocity at the cell centroid P and the velocity at the cell centroid N. So this scheme is second order accurate, which means that it will give us a good, some sort of good numerical solution. It will be the higher the order of accuracy of our interpolation scheme, the better. But one of its main disadvantages is that the numerical solutions that will be obtained using this scheme will tend to exhibit non-physical oscillations. That means that if you use the central differencing to solve these equations using the finite volume method, the numerical solutions that you obtain for your temperature or velocity or concentration field will exhibit non-physical oscillations. Also, this scheme can give you non-bounded solutions. That means that you will obtain solutions outside your domain, your physical domain. So this is not great for the accuracy of your solutions. So in order to solve this problem, some mathematicians, researchers have developed another scheme which is called the Upwind differencing, also called UD, where the values of the cell centroid, no, the values of the cell faces will be determined according to the direction of the flow. I will explain this. So in other words, the velocity at the cell faces will depend on the convective flux F, which you remember was defined here, before, here. So actually this convective flux, I mean, F is called like this in the literature, but if you obtain the units of this quantity, you will obtain a flow. So convective flux here, this product between brackets is the mass flux, the mass flux. But if you multiply by the surface, you will obtain a flow. So you just need to be careful with this notation. But yeah, F is called like this in the literature. But this quantity F is going to be useful to obtain the values of the velocity at the cell faces. So F has a physical meaning, as I was saying. It is related to the mass flow. So in this kind of interpolation schemes, we distinguish between cells. So here we have the cell with centroid P. So this cell is called the owner. And then the cell next to it is called the neighbor. So here, remember, we want to evaluate the velocity at the cell faces. We need the normal unit vector, and the vector UF is not necessarily the same in the same direction as the vector N. So that's why it's with a different color. And then remember, this face has a surface. So we use this notation, the owner, because if this quantity is greater than 0, that means that the mass flow will leave the control volume with centroid P. So if F is positive, the direction of the flow goes from left to right. On the other hand, if F is negative, that means that the flow will enter the control volume, the owner control volume. So that means that the direction of the flow goes from right to left. So this is important because the Upwind differencing is expressed in equation 15. So here we have the case where F is positive. So that means that, remember, the mass flow leaves the control volume. It will leave the owner cell. So the flow direction goes from left to right. So that means that in Upwind differencing, the value of the velocity at the cell face will take the value from behind. That means UF is going to be equal to the velocity at the cell centroid P. And let's say we were also interested in evaluating the velocity at this cell face. So if the direction of the flow goes in this direction, now UF2, which is the value of the velocity at this cell face, will take the value of the velocity UN. So yeah, you can see this equation 15. But now, if we have the opposite case, if the direction of the flow goes from right to left, here the velocity at this cell face, UF, will take the value from behind. So it will take the value of the velocity at the cell centroid N. And now, for this cell face, UF3, if we have this case, now UF3 will take the value of the cell centroid P. So that's just basically upwind differencing. So one of the advantages of this scheme is that it guarantees boundedness of the solutions. So that means we will obtain solutions within the physical restrictions of our system. And also another advantage of this scheme is that it avoids the presence of numerical instabilities, which is in contrast compared with the central differencing, where we tend to observe non-physical oscillations. However, the problem is that, in this scheme, the velocity or the value of the properties, either temperature or concentration, in this scheme, those properties does not vary linearly across the cell faces. So that means that we cannot use an equation like 12, where we assume a linear variation between the centroids P and N. So that means that for the Upwind scheme, we have only first order accurate. Remember that I say that the higher the order of accuracy of our interpolation scheme, the better. But in this case, this is only first order accurate. So there is another scheme that combines the good properties from the previous schemes that I described. So we have the blended differencing that was developed to preserve the accuracy of the central difference scheme, the CD, and this scheme also guarantees the stability observed in the Upwind difference scheme, UD. So for the blended differencing, which is equation 15, we evaluate the velocity at the cell faces using this equation, where UF-UD is the one for the Upwind difference scheme. So this term is the one from equation 16 or equation 15, and UF at CD is the interpolation scheme, the central difference scheme that is shown in equation 12. But we have another parameter, which is gamma, which is called the blended factor. Or it is also bounded between 0 and 1. And obviously, if, for instance, if gamma is equal to 0, we recover the Upwind difference scheme. But if gamma is equal to 1, we recover the central difference scheme. So in order to choose the appropriate factor, the appropriate value of the blended factor, the CFD software that you are using will let the user choose the scheme that determines the proper value of gamma. So obviously, the closer the value of gamma, if gamma is closer to 1, we will get mostly the properties of the central differencing. But if the value of gamma is closer to 0, we will mostly get the properties of the Upwind differencing. So yeah, so these schemes are the most common ones, but there are obviously much more schemes. And researchers, mathematicians, have developed new schemes to take into account the ideas of the previously described schemes. And their main goal, obviously, is to improve the accuracy of the interpolations. One example, another example, a simple example of interpolation scheme is the linear Upwind differencing, which is similar to this one, but now we will incorporate the gradients of the velocity at the centroids in order to improve the accuracy of the scheme. I'm not explaining this linear Upwind scheme here, but if you understand these ideas of central differencing, Upwind differencing, and blended differencing, you will understand those slightly more complex schemes. And there is also much more accurate schemes, which are called the high resolution schemes, which obviously their main goal is also to provide stability and even more accuracy in the solution of flow problems, where the nonlinear effects are highly important. Remember, the convective terms give the non-linearity to the conservation equations. So if you want to obtain good accuracy in your numerical solutions, it is highly recommendable to use high resolution schemes. And one example of such a scheme is the Cubista, which stands for Convergence and Universally Bounded Interpolation scheme for the treatment of advection. So this is a really, it's much more complex compared to the schemes that were explained here. But if you want to know more about this scheme, I recommend you to read this original paper by Alves that was published in 2003, where they explain the basics of this Cubista scheme. And I personally use this scheme in my previous research. This scheme is third order accurate, and I use it to simulate transient viscoelastic flows. So that means flows of fluids that exhibit both viscous and elastic properties. And yeah, if you want to read more about my research and about this particular interpolation scheme, I recommend you to read my research papers that will be included at the end in the references. And yeah, as I was saying, I use the finite volume method to explain how do we treat the convective terms. But in finite differences is really easy. I just want to give a brief example of how do we evaluate these convective terms. So one of the main differences between the finite difference method and the finite volume method is that the properties are usually evaluated at the cell faces. In the finite volume method, we were evaluated the properties at the centroids, but here in the finite difference method, we will focus on evaluating the convective terms at the cell faces. And let's say let us just assume the simplest case, where we have a 2D flow where the velocity field will have two components, and then this convective term can be simplified just as this one, this expression. We will only consider this one. We have the the derivative of this product between the velocity in x direction plus the product between the velocity in x direction and the velocity in y direction. So how this product varies in the y direction. So we will only focus on this first term, and then remember this convective term has to be evaluated at the cell phase, where I use this notation. So we have this cell which has location IG, but I want to evaluate the convective terms here at the cell phase, which has location 1 I plus 0.5 and then J. And then with equation 18, this convective term is evaluated using the finite difference method, which means we have to evaluate this product between the velocities at this location, which is at the cell center of this cell, minus this product at the cell center of this cell, divided by the distance, by the cell size, or by the distance between the cell centers. But remember, in the finite difference method, the velocities are not defined at the cell centers. So we have to interpolate these values of velocity using values of the velocities at the cell phases. So we will use central differencing, which is the interpolation scheme that I explained here. So we assume that the cell size is the same for all cells, so we use only equation 14. So remember, we have to evaluate the velocity here, but with central differencing, that means that we have to use the velocity at this location and the velocity at this location divided by 2. And for this cell center, we also use central differencing. So this equation tells us that we have to use the value of the velocity at this cell phase and then the velocity at this cell phase divided by over 2, and then we have these values. We use an interpolation scheme to evaluate the values of the velocity here and here, and then we substitute these equations here into equation 19, and then we will obtain an estimate of the convective term at this cell phase. So in finite differences, it's even easier to evaluate these convective terms using central differencing, and yeah, you can use also Upwind differencing, and it's really straightforward. And just to conclude, some references. So my main reference was the doctoral thesis of Dr. Hasek that was published in 1996 in Imperial College London. You also want to know about other high resolution schemes, I recommend you to read this paper by Alves. You can also find really good information in the Open Foam Programmer's Guide if you want to read more about interpolation schemes, or in the Rotool User Guide by Pimenta and Alves. That was is even more recent. And then in these papers, my research papers, where with my colleagues we simulate complex fluid flows, for instance, viscoelastic flows and shear feeding fluids. I use the Cubista interpolation scheme in this research paper. So you want to know more about CFD simulations of complex fluids of industrial interest, I recommend you to read these papers. So thank you very much for watching this video. If you have any suggestion, comment, please leave it in the comment sections.